We talked about the idea of a Taylor and a Maclaurin polynomial, and we've gone through the idea of a power series. And what we really want to do is we want to mix those two ideas together and talk about the idea of a Taylor and a Maclaurin series. So a Taylor series or Maclaurin series is really just a power series that ends up being a Taylor or Maclaurin polynomial. Now, you'll recall that a Maclaurin polynomial is always centered at 0, but a Taylor polynomial can be centered at any arbitrary value. So it's the sort of the more general term of that. And the qualifications to get a Taylor polynomial for a function in mathematical terms, they're exceedingly rare. You never find functions like this. But in terms of physical processes and most things that we see when we model real-world phenomena, we actually almost always get it. So it's kind of a disconnect between the way mathematicians study it and the way that like physicists would study it. But anyway, if you take a look at the functions, if you take some function and if it has derivatives of all orders, what does that mean? That means that its first derivative exists, its second, third, fourth, fifth, 10th, 100th, millionth, right? It continues to be differentiable all the way. If it always has a derivative at this point, then we can actually write that function as a Taylor polynomial, and specifically a Taylor polynomial that has an infinite amount of terms. And it's a power series because it's x minus the center to a power, and then that a sub n, that that little coefficient that a sub n, is determined by this exact formula, I guess is the right word for it. And what you do is you take, for the first, or for the 0th term, you take the 0th derivative of the function. That just means you don't take the derivative of the function, and you evaluate it at the center point, and then you divide it by the 0 factorial. So that's what happens here. Now for the first term, you have the first derivative evaluated at the center, divided by 1 factorial, and then you have x minus c here. Second derivative evaluated at c over 2 factorial, and so on and so forth. This simplifies to these things here, right? 0 factorial is just 1, and then this to the 0 power is also just 1. So our first term is just the function at that point, which is kind of nice. It basically says that the function is approximated by the function value at that point, and then a bunch of polynomial terms from there. And you'll see that those polynomial terms increase in degree. So the more terms that you use, the more complex the polynomial becomes, and therefore the richer it can approximate it by. And a lot of what's nice about a lot of physical processes and physical models is that you don't have to do an infinite number of terms to get close enough. You can do an approximation with, let's say, 10 or 100 terms. And there's something called Taylor's theorem that I'm not going to go into right now that describes how good your approximation is. Essentially, it really is describing how bad that approximation is if you stop here. It says, okay, if I do 10 terms, how bad is my approximation? Well, if you say, well, it only has to be, as long as it's within 0.01 of the right answer, I don't care, then we can use Taylor's theorem to say, okay, well, it's always going to be within that as long as you stay here. So it can kind of tell you how many terms you have to get your right precision. It's a really useful tool because I don't want to generate an infinite degree polynomial. So the question then becomes, okay, that's great. I've got this formula. How do I make one of these? How do I actually generate a infinite series, right? Because I don't want to generate an infinite number of terms, and I don't even know what a generic version of the nth derivative looks like. So your process kind of has to go like this. It's kind of annoying. You have to generate a sequence of terms, start to notice a pattern, and then develop a guess at that pattern. Now, there are more advanced mathematical techniques like mathematical induction. Mathematical induction is a logical technique that allows you to actually prove your guess. But here we're not really going to go into that because that's a little beyond what we study at this level. But the idea here is we want to generate it, start to recognize a pattern, and then generate an arbitrary or a generic nth term. So anyway, let's take a look at a pretty well-behaved function. That's the function sine of x. And we're going to use the center value of 0. So this is going to be a Maclaurin series, not, I mean, it's a Taylor series, but it's specifically a Maclaurin series. So what you do is you take the derivatives. So we're going to take we have the original function, we take the first, second, third, fourth, and fifth derivative, and then of course this is considered the 0th derivative. And then all we do is we evaluate it at that center point. Now remember that center point is 0. So this sine is with derivatives is actually periodic as well. What you notice is that the first derivative is cosine, the second is negative sine, the third is negative cosine, and then you get positive sine. But these are the same, so you're always going to end up in a 4 cycle where the fifth matches the first, the sixth matches the second, and then it continues on from there. So you really only need to generate a few derivatives to kind of see the pattern. Or even if you needed to generate more, you don't actually have to like work at it, you can just copy it. So if we plug in 0 for sine, we get 0. 0 into the cosine function gives us 1, 0 into the sine function gives us 0, 0 into the negative cosine function gives us negative 1, and 0. So I start to see a pattern, 0, 1, 0, negative 1, 0, 1. So it kind of looks like an alternating series, but it's not just alternating term to term, it's actually alternating every second term. The 0 terms are going to make this thing disappear. If we plug into, so if we look at our formula here, we take the function, and then really it's just a function, right? These become ones here. So the function, the first derivative, second derivative. If you follow the pattern here, you're going to get, well, that's 0, 1, 0, negative 1, 0, 1, and then on bottom is just an increasing number. You probably can't see an increasing factorial value 1, 2, 3, 4, 5. And then because it's a Maclaurin series, it's not x, it's just x. So it's x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, and so on. If I notice here, anything that has an even power is always 0. Okay, so that tells me that I have only odd powers left. So I have, this is over 1 factorial, but then it becomes negative, and then it becomes positive. And if you generate even more terms, you would get another negative at 7th power, and another positive at the 9th power. So, all right, this tells me I've got kind of a pattern going. It's hard to figure this out though. I've got an alternating series, so I know that my alternating series is something like negative 1 to the n. Okay, negative 1 to the n. That's pretty useful. But I also know that I'm skipping by 2 each time. So I'm skipping by 2 each time, so I have to do 2n, because this is my skip value, but I start at 1. So this is my starting value, and this is my skip number. That's kind of how you do that arithmetic progressions. You have a starting value, and you have a skip number. Well, I noticed that these numbers also match. The power on x and the factorial power match. So if this is 2n plus 1 factorial, the power also has to be 2n plus 1. Now notice this matches if I have n equals 0, that if I plug everything into there, that becomes 1, that becomes 1, this just becomes x, which is what this term is for n equals 0. And then for n equals 1, I get negative x cubed over 3 factorial, so that's this. So we're kind of re-indexing. We're not using the n's that you would think of here. We're creating kind of a new index. It's kind of difficult to say. But anyway, now that I have this generic term, what this tells me is I can write this as a power series here. And you might ask yourself, okay, why is that useful? I can plug in sine into my calculator. Okay, great. How do you think your calculator gets you sine? Like, what do you think it's doing? You think it's got something underneath that's just some sort of like magical sine box that says, no, it actually has a little more sophisticated algorithm than this, which is even more interesting. But supposing you didn't have a more sophisticated algorithm for sine and you had to generate it. Well, now I have a polynomial, and I know how to compute polynomials. For whatever number I plug in, I know how to square things, I know how to cube things, I know how to take them to the 5th power, and I know how to compute factorials. So it takes a function that is kind of this black box, like a sine function, like who in the world knows what this looks like, and converts it to a polynomial function, something that's extremely well understood, right? You know about the turns and the end behavior and all that kind of stuff. And so you get a really nice approximation with something you understand for something that can be kind of a black box. And this works even better when it's functions that you don't have a good idea about what they're supposed to do or supposed to look like. Like sine, hopefully you're familiar with that, but you might have functions you're not familiar with, and this is a really, really powerful technique to generate an equivalent representation of a standard function.